Welcome to the deep dive. Today, we're going way beyond the typical security conversation. We spend so much time talking about information technology, IT security.
Right, protecting emails, user data, that sort of thing.
Exactly. But today, we're moving into the physical world. We're talking about the critical infrastructure that keeps the lights on, keeps water flowing.
We're talking about operational technology, or OT. This is all about securing the heavy machinery itself, the actual valves, pumps, and control systems that run our world.
Okay, so let's set our mission for this deep dive. We really need to understand why the entire security playbook gets flipped on its head when a failure means a physical explosion instead of, just a data breach.
That's the core of it. The risk models are totally inverted. In IT, a bad day is usually financial. It's fines, maybe identity theft. In OT, a bad day is physical.
It's a pipeline bursting.
Or power grid going down. It could be catastrophic infrastructure failure or even serious injury. You have to completely recalibrate how you think about risk.
And this is where the sources get really interesting right away. They point to this core difference in philosophy. For decades, IT security has been driven by the CIA Triad.
Confidentiality, integrity, and availability.
With confidentiality, keeping secrets, almost always at the top of the list.
But in the OT world, that whole thing gets inverted. It becomes AIC.
AIC. So availability and integrity come first.
They dominate everything. Confidentiality is a distant third. And that right there is the foundational shift you have to grasp.
All right, let's break that down. Availability. Why is just keeping the system online the absolute #1 priority?
Because the process must continue.
Yeah.
I mean, think about a blast furnace or a chemical plant.
You can't just turn it off.
You can't. If you stop the system abruptly, you don't just lose money, you can cause massive physical damage. One of the sources had a great line. You cannot reboot a blast furnace for a 2-hour Windows update.
Right. The update has to wait.
The process flows. Downtime isn't just an inconvenience, it's potentially a catastrophe.
Okay, that makes perfect sense. And then integrity is right behind it. It's not just that the system is on, but the information it's using has to be, well, true.
Exactly. Integrity is all about whether you can trust the data. If a pressure sensor is reporting 50 psi,
but an attacker has made it, say, 50 TSI when it's really 500.
You're headed for a disaster, a physical one. The attacker doesn't even need to inject new code. They just need to make the system lie to itself. Compromised data integrity leads directly to physical failure.
Which leaves confidentiality at the bottom. I guess if someone reads the temperature in a water tank, it's not great, but it's not nearly as bad as them changing it.
Precisely. The data itself, the flow rate, the temperature, that's not the secret. The secret is the ability to control the physical action. And for a long, long time, the industrial world protected these systems with a comforting myth.
The air gap.
The air gap.
This idea that the OT network, the one running the machinery, is totally physically disconnected from the internet and the corporate network.
It's the lie we tell ourselves to sleep better at night. Because in reality, that gap is bridged all the time.
How?
Oh, a vendor needs to do remote maintenance, so they drill a hole, a permanent connection, right through the firewall. Or a contractor comes in and plugs a USB stick into a control station.
And suddenly malware from an office environment is on the factory floor.
And your so-called isolated network isn't isolated at all. The air gap is gone.
So if these systems aren't truly isolated, how are they supposed to be structured? I mean, you can't just have the HR server on the same network as the controls for the power grid.
No, and that's where segmentation is absolutely essential. This brings us to a foundational concept in industrial control systems. The Purdue model.
The layer cake.
Yeah, that's a great way to visualize it. It's a stack, a model designed to create stricter and stricter security zones as you get closer to the actual physical process.
Okay, so walk us through the layers. Let's start at the top, the safest part.
Right, so level 4 is the top. That's the enterprise network. It's your standard IT, world corporate email, HR, finance.
All the stuff that gets hit with phishing attacks.
All of it. And the funny thing is, this is the most forgiving layer. If it gets breached, you lose data, you lose money. Bad, but not physically destructive.
Then there's a buffer zone, right?
That's level 3.5, the DMZ, or demilitarized zone. This is a critical separation layer. It's designed to be a one-way security checkpoint, making sure that traffic from the messy corporate side can't get direct control of the assets below.
And below the DMZ is where the real action starts.
Level 3, the control room. This is where you find the operator workstations, the HMIS human-machine interfaces.
The screens where a person clicks a button to open a valve.
Exactly. And from here, the risk just skyrockets because below that are levels 1 and 0, the process layers. These are the PLCs, the programmable logic controllers, and the actual field devices, the pumps, the motors, the robot arms.
And if an attacker gets down to level 0 or 1,
Game over. That's when you cause an immediate uncontrolled physical event. You can tell a PLC to overpressurize a pipe or shut down a cooling system. The closer you get to the metal, the more immediate and destructive the hack.
this is all compounded by what the sources call technical debt, right? This huge weight of using ancient technology.
Staggering amounts of it. Many of these core industrial protocols, they're insecure by design.
Why? I mean, that sounds crazy.
Well, it's not because the engineers were careless. It's because when protocols like Modbus or DNP3 were invented back in the 70s and 80s, security just wasn't a design requirement. They were built for speed and reliability in what was assumed to be a closed, trusted system.
So they stripped out things we'd consider essential today.
Absolutely. Zero native encryption. Zero authentication. If an attacker can get on the wire, if they can just physically or logically connect to that network, they can send commands. No password needed. The system just trusts it.
The sources even point to the terminology in Modbus, the master-slave architecture.
Yes, and that perfectly illustrates the problem. The master device sends a command, like open valve 5. The slave device, the actual controller on the valve, has to obey.
No questions asked.
Instantly and without question.
Yeah.
It's brilliant for speed, but it means if a hacker can pretend to be the master, they have instantaneous physical control of your plant.
And we can't just rip all this old stuff out because of this technical debt idea.
It's a massive problem. You have critical infrastructure running on Windows XP, even older systems.
Yeah.
You can't just patch them. The machine it controls might cost $10 million, or the company that made it went out of business a decade ago. Trying to update it might crash the whole process.
Violating that #1 rule, availability.
Exactly. So you're stuck.
So you've got these vulnerable, unpatchable systems, theoretically protected by an air gap that we know is a lie. It's not surprising the threat landscape is changing. What are attackers actually doing in 2024, 2025?
The goal has shifted. It's moved decisively from theft to disruption, to physical destruction. We could look at 3 really clear examples of this. First up, Volt Typhoon. This is a Chinese state-sponsored group. Their signature technique is called living off the land.
Living off the land. That's a fascinating phrase. What does it mean in practice?
It means they don't use their own flashy custom malware that an antivirus might spot. Instead, they use the tools that are already built into the system they're attacking.
Like what?
Legitimate tools, like PowerShell on Windows. They use the system's own utilities to carry out their commands. This lets them blend in with normal network traffic and stay hidden for, well, for years sometimes.
And what are they doing while they're hiding in there?
They're pre-positioning. The sources are clear on this. Volt Typhoon has embedded itself deep inside U.S. critical infrastructure power, water, communications. They're not stealing data. They're dormant. Waiting for the order to flip the switch and cause widespread blackouts in a future conflict. It's about strategic disruption.
That's terrifying. Then there's something with an even more malicious goal, this thing called Fuxnet.
Yeah, Fuxnet was different. It targeted Russian IoT sensors in 2024, and it was just purely destructive. This malware wasn't designed to steal data or ask for a ransom.
What did it do?
It was engineered to physically brick the hardware. It burned out the memory modules on the chips themselves, a permanent denial of service.
Permanent.
As in, the only way to fix it was to physically go out, find the fried chip, and replace it. That's not cyber warfare anymore, that's straight-up sabotage.
But maybe the most shocking examples were the water wars. These weren't even sophisticated attacks, were they?
Not at all, and that's what makes them so scary. Instance in small towns like Muleshoe, Texas. The attackers, calling themselves the cyber army of Russia Reborn, weren't using some secret zero-day exploit.
So what did they do?
They just scanned the internet. They looked for the control screens, the HMIs for water utilities. They were connected directly to the internet through things like VNC, a remote desktop tool, and they found that many of them had no password.
Wait, no password. You're telling me they could just log in, see the control panel for a town's water supply, and just start clicking buttons?
That is exactly what happened. They were overflowing water tanks, changing chemical settings, just by clicking a mouse from thousands of miles away. Because the physical controls were exposed to the public internet with zero authentication.
The barrier to entry for causing real physical damage is just terrifyingly low.
If you ignore the absolute basics, yes.
Okay, so given all this delicate legacy systems, aggressive attackers, how do you defend these places? You can't just run a normal vulnerability scan.
You can't. That could crash the whole system. So the OT defense playbook is all about visibility without interference.
Let's talk strategy one, passive scanning only. Why is this so important?
Because an active scanner, something like Nmap, is loud. It sends out a flood of packets to see what's on the network. A modern server is fine with that. A 20-year-old PLC might see that traffic as an error and just fall over.
You've stopped the assembly line again.
You violated the first rule. So the passive approach uses tools, like from Dragos or Nozomi, that just listen. They're like a silent observer on the network. They see all the traffic, identify the devices, spot vulnerabilities, but they never send a single packet to the sensitive equipment. Okay, so you get visibility without risk. What about defense strategy 2? This one sounds physical. Unidirectional gateways or data diodes.
This is the ultimate reinforcement of the air gap. It's a hardware box that uses physics, not software, to enforce the rules. Inside the box, data is converted to light. It can only transmit in one physical direction. So data can flow out of your plant for monitoring, but it is physically impossible for any data, any malware, to flow back in.
Even if the entire corporate IT network is on fire.
The laws of physics prevent the attack from crossing back into the OT network.
That sounds foolproof, but is it practical? I mean, are these things everywhere, or are they just for, like, nuclear plants? Historically, they were for the highest risk places, yeah. They're an investment. But the cost of an outage is so high now, and the threat is so real, that we're seeing them deployed much more widely. It just removes a whole class of risk.
And finally, what do you do about that Windows XT machine you can't touch? Strategy 3, virtual patching.
Right. Since you can't patch the box itself, you protect it from the outside. You put a smart firewall and intrusion prevention system right in front of the vulnerable machine.
And this firewall knows what attacks to look for.
It knows the specific exploits for that old version of Windows. It inspects all the traffic heading for that machine, and if it sees an attack, it just drops it. The exploit never even reaches the target. It's like an external virtual patch.
This whole deep dive really lays it bare. The challenges in OT security are just. They're on a different planet from IT. Availability and integrity are everything because failure is physical.
And the threats are now geopolitical. They're patient. They are aiming for disruption.
So to bring this all back for you, the listener, understanding this isn't just an academic exercise. It should fundamentally change how you think about risk whenever the digital world touches the physical one.
Securing critical infrastructure is a matter of physical safety. It's not about data privacy.
Exactly. If the data is kept confidential, but the building burns down, you've failed. And that leaves a really important question for you to think about. We've seen how OT flips priorities like patch immediately. What other common IT security assumptions need to be completely reevaluated when you're dealing with real-world physical consequences, say in an autonomous car or a medical device? Something to consider as you navigate that line between the data world and the world of physical control.